Okay, today we'll start to talk about Lecture 7. So these are the papers that the UC Berkeley instructor asked his students to read. If you're interested, you can read this paper and raise questions to me. Now, the outline of Lecture 7, instruction level parallelism, compiler techniques to increase ILP, loop unrolling, and etc. Okay, recall from pipelining review, pipeline CPI is the ideal pipeline CPI plus those stall cycles due to hazard avoidance. Okay, so there are hazards. Hazards may not cause a problem in certain pipelining implementation. It's just like a precaution. It's just like a warning. So if your pipelining is not designed properly enough, then something wrong will occur. But it doesn't necessarily happen in any implementation. Sometimes, due to data dependencies, we need to stall the CPU for certain cycles. And when we do the stalling, how do we do? Stall the entire CPU? No, we let the older instructions to proceed, but stop the newer instructions to wait for some result to become available. Okay? What about structural hazard? We do the same. Let some to proceed as usual, and the others competing for the resources but are newer in the instruction stream to wait. Okay, for the control hazard, still the same. So there are stall cycles due to structural hazard, due to data hazard, due to control hazards. So what is ideal pipeline CPI? That's the measure of the maximum performance attainable by the implementation, assuming everything is idealized. No data dependence at all, no structural hazards at all, no control dependencies at all. So the CPU can run at the maximum speed. And we don't do any multi-cycle instructions like multiplication, division, nothing like that. Then that's the idealized pipeline CPI. Okay, I should say that's the peak CPI. And structural hazard, you already understand what these are. You know what these are and what these are, so I will not repeat. Okay, instruction level parallelism means overlapping the execution of instructions. When I say instructions, are these instructions dependent on each other? The answer could be yes or could be no. Okay, so instruction level parallelism can be utilized in two different forms. The first form is like this. If this is the time axis, instruction parallelism could mean this. The other one could take more time or less time, doesn't matter. Or it can mean something in this form. Simply partial overlapping. This is like complete overlapping, right? At least one is 100% in parallel with the other. But for this one, none is 100% in parallel with the other. Yet we still can call this a kind of ILP. Okay, so it becomes somewhat confusing. When we talk about pipelining, why don't you use the term ILP? Well, we should have, but ILP in a limited sense could mean only this. But in a broader sense could also mean this. So when people mention ILP to you, make sure you know what he means. Okay? Okay, there are approaches to exploit ILP. Very simple categorization. One is rely on hardware, and the other is to rely on software. Next, we define basic block. What is basic block? Do I need to define any further for you? No? Okay. So in a basic block, what do you think about the degree of ILP in a basic block? Should be very limited, right? So average dynamic branch frequency is 15% to 25%, meaning basic block size is like from 4 instructions to 7 instructions. Okay? So instructions in basic block are likely to be heavily dependent on each other. So ILP in basic block is very limited. To obtain substantial performance enhancement, we must exploit ILP across multiple basic blocks. In order to talk about this, I need to ask you one question beforehand. Is it easy to exploit ILP within a basic block? Is it? Tell me if it is easy. Not easy. So tell me why it's difficult. Okay, let me give you the answer. Relatively, it's very easy because this code piece is known beforehand. Plus, there are not many instructions within this sequence. Okay, so relatively it's easy. Okay, but there's no sufficient amount of ILP exploitable. So next thing we need to do is to exploit ILP across multiple basic blocks. Is it easy? That's the first question I want to ask you. Next question is it easier to do it in software or in hardware? That's the second question I want to ask you. You think in software it's easier? Anybody favor the hardware approach? If you favor the hardware approach, please raise your hand. Okay, if you favor the software approach, please raise your hand. You don't have to anymore. 1, 2. What about the other 4 students? 3? What about the other 3 students? You're just sitting here, listening, without using your mind? Have to have some judgment. Okay, so let me tell you, software approach is very difficult because whenever I encounter the branch instruction, usually it's a branch if. What if it's a branch always? Then I can extend the basic block to contain both basic blocks if it's a branch always, right? So software is not afraid of branch always, but what if it's a branch if? Then you should exploit ILP of both the top basic block and which succeeding one. The yes case or the not case basic block, you don't know. Very difficult. Yet for the hardware, it is also difficult because I need to remember what have happened. In other words, what instructions I have executed, particularly what destinations they're going to produce, right? When this destination will become available, plus I need to foresee the upcoming instructions and particularly what sources they want to use in order to detect dependencies. What dependencies? Data dependencies. What about control dependencies? I don't care. Within the basic block, there's no control dependence. But I need to remember the ordering of the instructions. The ordering of the instructions is also a kind of control dependencies. Who is older? Who is newer? Right? Okay, so hardware has its difficulties, software has its difficulties, and the argument of whether we should do this in hardware or software still goes on. Okay? So later we'll see some current approaches. But let me go on. Okay, so we must explore IOP across multiple basic blocks. Next, simplest is loop-level parallelism. Loops are easy to deal with because 90%, maybe 99% of the time, the loop will iterate back. Okay, so if you do speculation or prediction, it's very likely that you'll be right. Okay, so loop is easier to deal with. Other methods to deal with loops, which is deterministic, not speculative. Well, we'll talk about that later also. Okay, so for this loop, it will loop for how many times? From here, I know I increment every time, and from here, I know it will iterate for 1,000 times. Okay, and within the loop body, we have arrays. We do the array operation. Okay, so let's study loop-level parallelism first because this is the easiest, and usually this takes up the most of the execution time. So this is the easiest, and this is also the most important. Unrolling. You know what unrolling means? Let's go back to the previous example. Unrolling means the loop body of this loop is only one statement. Remember, this is high-level statement. In assembly, there might be several statements. Well, it doesn't matter. And this loop will iterate for 1,000 times. During these 1,000 iterations, everything can be predicted. Nothing will change. Okay? So what if I do 2 elements within the loop body and let it iterate for 500 times? We can do even better. Let the loop body do 3 elements and iterate for 333 times, and so on. Okay, then aren't we getting a bigger basic block? Would there be more instruction level parallelism? The answer is yes. Imagine the assembly code of this statement. You need to do load and then add. Remember, load takes time. Usually load will cause stalls, right? So if you have more of these, then perhaps you can do load of I, and then load of I plus 1 element, and then load of I plus 2 elements. And then by the time we've finished issuing this instruction, when we are ready to issue, add I plus I equals to I. This, I just show the indices, okay? When I'm ready to issue this instruction, these 2 loads should have already committed. No more stall cycles. Okay? So that can enhance my pipeline ILP. Better yet, all these loads are data independent with each other, which also gives me more ILP. Okay? And then we have unroll the loop body for how many times? In our case, we have unrolled it 3-fold. So the number of iterations will now 1/3 of 1,000. In other words, 333. Okay? Whoops. We have 1 iteration left out. What should we do with that? Okay, use prolog code. Add in some code to do the first iteration and do the rest 999 within the loop body. Okay? So that's the so-called loop unrolling. Okay, so loop unrolling can be done via dynamic branch prediction or static. Is this dynamic or static? Assuming that this is the time axis, tell me if this is a result of dynamic or static loop unrolling. Come on, use your mind. Give me a guess. What? Static? Any other guess? It's safe to follow that guy's idea. Could that be dynamic? Okay. From this execution sequence, actually, could be both. Actually, it could be both. But if it's dynamic, then along the time axis, before we can do this, we must do branch prediction somehow, somewhere. Okay, remember, here, if we're exploiting ILP, there could be multiple instructions executed in parallel. Okay, so if we simply look at loads and adds because they have data dependencies, then it's like this, but there could be something else executed along the time axis, along the line. Okay, so it could be both, but you need to know how that could happen. Okay, so static is more like the answer. Yes, but could be dynamic. Yes. Dynamic means we have a very aggressive instruction fetcher. So it knows what the future instructions will be. And then, of course, these instructions need to be decoded in order to, for us to know what they are and do whatever is appropriate. Like we found out there's a branch in the upstream. Then we predict the outcome of the branch such that we know how to divert our instruction fetch flow and fetch the likely instructions in the future. Okay? Do whatever you can. Do whatever your competitor cannot to make your design more competitive. And we are always in such a game, whether you're a student or you're in the marketplace. Okay, so dynamic will help, and static can do the same. Another way is vectors, to be covered later. So we can also use, for the loop like that, we actually can use one simple vector instruction to do it all. Don't need to do branch if all the time, wasting time and power. And determining instruction dependence is critical to loop level parallelism. Then, if two instructions are parallel, then that means they can execute simultaneously in a pipeline of arbitrary depth without causing any stalls. So here, this definition is somewhat narrow in mind. It says parallel means no dependence at all. Can be executed simultaneously in the pipeline, means no data dependence. Simultaneously in a pipeline of arbitrary depth can be 100 stages. So this means no data dependence, no structural dependence, and of course no control dependence. Okay, or dependent, they are not parallel and must be executed in order, although they may often be partially overlapped. So the pipelining falls within this category. And here, the author doesn't think that this is the so-called instruction level parallelism, ILP. So pipelining here is excluded from ILP. Yet, in some places in the textbook, pipelining will be included in the ILP. So you need to really understand what's happening in order to be able to do conversation with the other peer researchers. Okay? Sometimes you think you're right. Maybe your teacher says, no, you're wrong. You need to understand why your teacher thinks that you are wrong. Okay, data dependence and hazards. This is an easy example. So these two instructions has data dependence. Here we deal with only true dependence. So that these two instructions cannot be executed simultaneously. Data dependence in instruction sequence this must be the instruction execution sequence. This must abide by follow the data dependence in source code. This source code should mean machine code. Remember, our CPUs will scramble your machine code and execute your machine code in some unknown order. Okay? So this instruction sequence means the execution sequence. And this machine code sequence, again, must abide by the original data dependence relationships from the application. Okay, so we also call the true data dependence the read after write dependence. And whenever there's a dependence, whenever there's such a dependence, do we say there's a hazard? Whenever there's a dependence, do we say there's a hazard? Yes or no? You think that's yes? Why? Okay, you think that's no? Then you want to add in other requirements in order to call that a hazard? Try. Try it.
I'm not sure.
You want me to give you some hint? Okay, so if this is our instruction execution sequence, okay, this is what really happens during my execution. And this instruction writes to R1, and after hundreds or even thousands of cycles, this instruction reads from R1. And suppose we're lucky enough that nobody writes R1 anymore between these two instructions. There could be other reads, I don't care. But what I care about is this is the last write, and this is far behind the read. Do we think this is a hazard? Probably not. Then what can be called a hazard? I think you already have some picture, very blurred picture on your mind. Okay, let me tell you. If they're close enough, if this read is close enough, then I will call that a hazard. If they're far apart, then I will not. So there comes another question. What do you mean by close enough? 1 centimeter away, or 1 meter away, 1 kilometer away? What do you mean by close enough? Okay.
On the pipeline depth.
Right, very good, very technical answer. Depending on your pipeline depth, then I can tell you what means close enough. Like if my pipe stage is 10, I'm not sure what each stage does. But if any write and read distance is within 10, then I say there might be a hazard. More than that, don't worry, okay? Is that a good hypothesis? Should be. Okay? Okay, so hardware and software must preserve program order. What does that mean? No, it doesn't have to preserve program order, but it just have to preserve the result, which will be the same as the if the program were executed in the original order. Okay, so I rather say must preserve the results. Okay, so program order means order of the instructions which would execute if executed sequentially as determined by original source program. You see, this source program means machine code program. Okay, if the program were executed in the original order, the result should be the same, even though if you want to do some scrambling, the result should still be the same as if the program were executed in original program order. So all the data dependencies are determined according to the original program. And presence of dependence indicates potential for a hazard. But the actual hazard and length of any stall is property of the pipeline. Okay, now does this sentence make a lot of sense to you now? Is it clear now? Okay. And the importance of the data dependence indicates possibility of a hazard and determines order in which results must be calculated and sets an upper bound on how much parallelism can possibly be exploited. Okay, so we're looking at all the dependencies, not just the dependencies caused by a certain register. Okay, all the dependencies caused by all kinds of instructions. Okay, so hardware software goal should be the same. Exploit parallelism by preserving program order only when it affects the outcome of the program. Okay, so when you exploit parallelism, you can scramble any instruction as long as they don't have data dependence, control dependence, structural dependence. Okay, but if in case they do, then you have to preserve program order. Okay, name dependence. So we want to write to R1, but this R1 will be read by a previous instruction in program order. In program order, what if in real execution order this instruction gets executed before R1 is read by the subtract? Then perhaps this instruction will read off a wrong value, an updated value, right? So why is that? Okay, the only reason for that is because this add instruction wants to use that place for its result. Can you use another place? Like if I give you another register called RA, and in the subsequent code, all the R1 should be replaced by RA. Will that generate the same program result? Yet you can scramble the order of these two instructions? The answer is yes, okay? So this is actually due to we decided to share the same room for these two instructions. What do I mean by same room? Oh, that's a kind of structure. So this kind of data dependence is in nature a structural dependence, not really data dependence, okay? Because you don't have enough number of hotel rooms, or you assign your hotel rooms to the customers in a too conservative way. Okay, so this is really a structural dependence. Same thing for the output dependence. Okay, there must be some other instructions in between using this R1. Otherwise, the calculation of this R1 is meaningless. But anyway, these two instructions compete for the same hotel room. Why do I say they compete for the same room? Because the execution can be arbitrary. Okay? So there might be competition. Okay? So why let them compete with each other? Why don't you let add use another hotel room such that there will be no dependence at all between these two instructions? Okay. Have you found out that we hate any kind of dependencies? And the only dependence which can never be challenged is what? We have three kinds: data, control, and structural. What is the only kind of dependence that we cannot challenge? Data dependence. That's the command from the user. Customers are always right. Okay? Okay, all the other dependencies are created by us, the system designers. Okay. What kind of persons are involved when I say system designer? Somebody tell me. CPU designer, of course. Anybody else? Anybody else? Compiler designer, yes, compilers are not that smart. So even if I give the compiler 64, 32 registers to use, usually a not too smart compiler will only use the first few registers. When I say not too smart compiler, I mean those commercial compilers. We've checked the IBM code, we've checked the Intel code, machine code, and found out that only a few registers are effectively used. Okay, although theoretically, compiler can use them all, but in reality, it's very difficult. If we have time, perhaps not in this course, I'll talk to you about compiler design, about register allocation, register assignment, and then you will understand, and then you will hate to have too many registers. Okay, so output dependence, you should have known all these already. It's write after write. Anti, it's write after read. True, it's read after write. Okay, first you write and then you read that written result. So only true dependence is data dependence. The other two, sometimes we call them data dependence, but sometimes we call them structural dependence. In nature, they are structural dependence. And I'll tell you how to solve this problem. Okay, control dependence. Every instruction is control dependent on some set of branches, and in general, these control dependencies must be preserved to preserve program order. So, do you know what is a control flow graph of a program? The control flow graph of a program looks like this. This is the first statement of your program. So, if this is a basic block of the first statement, then this is the first control flow graph node. Every node stands for a basic block. And then maybe there is a branch always. Maybe there is a branch if. It is a good practice to use only two-way branches in your instruction set architecture. Okay? Although high-level language may have this kind of branch. What is this kind of branch? Case or switch statements. Okay, we can also implement that kind of instruction at lower level, but it's not encouraged. Okay. So, a good practice is to use only two-way branches. And this may be two-way, this may be always, and so on. So this is the so-called control flow graph. The execution of a certain instruction within this basic block is dependent on what? On this branch and this branch and this branch and this branch. It depends on a sequence of branches in order for us to get to here. Okay, so that's what this statement says. So S is control dependent on P1. In this case, it's control dependent only on one statement. And S2 is dependent on which one? Okay. So control dependence need not be preserved. Why? I thought the author says it needs to be reserved. Okay, willing to execute instructions that should not have been executed, thereby violating the control dependencies if can do so without affecting correctness of the program. Okay, so you don't need to preserve control dependence if you can guarantee the correctness of the final result. What does that mean? That means you can do whatever you want. You can do any redundant work. Remember, our chip has ample, too much resources. Use them whenever you like. Be my guest. Okay, so you can do whatever you want in any order as long as you still have the ability to guarantee the correctness of your final result. Okay, so you can do all the redundant work, try all the control flow paths. Okay, as long as that can make your program finish early. That's what our customers want.
In reality, that would be hard to do in hardware.
It's not hard. Just try in all the paths. Okay? If you don't care about your electricity bill. There was a time in which we didn't care about the electricity bill. But it was a long time back. Okay, so you know the idea, you know what the author is trying to tell you. So instead, two properties critical to program correctness are exception behavior and data flow. Data flow, we already understand what that is. Exception behavior, I talked to you about that before. Let me see if you still remember. Okay, in a pipeline execution, if some exception occurs here, don't be in a hurry to handle it, because later you might have another exception occurring here. And this may be the exception that you should handle before dealing with this one. But still, please be patient, because there are yet 3 other instructions which are not completed in your pipeline. You should wait for the bigger brothers, bigger sisters to commit first before you do any handling, exception handling. So exception behavior is very difficult to deal with, okay? Now, do I need to extend the same discussion to having multiple pipelines in the design? No need. Okay, the considerations will be the same. Okay, we look at exception behavior. Preserving exception behavior, any changes in instruction execution order must be changed how exceptions are raised in program. I'm sorry, must not change. So these instructions, I made an assumption. They are executed in program order. What if they're not? For example, this is instruction 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, whatever. So how do I know which exception belongs to the oldest instruction? Any way to tell in the pipeline? Given all this information? The answer is no. No way I can tell. So, do we need to be able to tell? Yes, that's a very rigid requirement. Then what can we do? What can we do? Give me some idea. Yes?
But we can keep a flag or instruction, account.
Oh, okay. Okay, something like we record the program counter of every instruction. That would do, right? Or do we have smarter ways? I don't know. You need to try all the possibilities in order to figure out a most economic and effective way, okay? So let me tell you what we are doing today, which may not be the smartest, but so far this is the best way we have discovered. That is, if this is my CPU, since I want to scramble the order of execution, so if this is my fetcher, here, I put a big table to record the order of my fetch. Record the order of the instructions that I fetched in. Okay? So whenever I fetch a new instruction, I add it to the tail of this table. Whenever, you see here we have decode, execute, write back, memory, whatever stages we have. Whenever an instruction commits, then we come back to the table and eliminate the corresponding record. Okay, so in this table, do you see what we have? All the instructions which are alive in my CPU, arranged in program order. Not in program order, in original program execution order, okay? So, will you dare to do like branch prediction? Okay. Suppose this instruction is a branch and you don't know how to fetch newer instruction from. You don't know which way it will go. But you do want to fetch more instructions in, right? We need more basic blocks in order to exploit instruction level parallelism. Okay, so you speculate, you guess according to your best knowledge that this branch will be taken. If that's the case, then you record a small flag saying taken, and then continue to fetch instructions from the taken path. Okay, so here your second basic block instructions are coming in. Later, your third basic block instructions are coming in, and then fourth, fifth basic blocks. In 1993, when the first Pentium processor is released, guess how many basic blocks do we have in the CPU at the same time? Give me a guess. That was an ancient processor. Almost 30 years ago, 20 years ago. Released even before you were born. And about 5, I don't remember the exact number, about 5 basic blocks were already active in the CPU. In other words, I made branch speculation 4 levels, okay? How accurately can you guess the outcome of a branch? Say 90%, okay? If you are 90% correct, you think that's good enough? Let's see. So I said 5 levels. In other words, 1, 2, 3, 4, 5. In other words, I made 4 speculations. If this is 90% correct, then this will be 81% correct, okay? The square of 90%, okay? And this will be 73%. This will be, I don't know. Very soon, the correctness, the rate of being correctness will be below 50%, okay? Even lower than arbitrary guess, okay? However, if the correctness rate is 98, that's what we can do today. Then later, it's 96, it's 94, it's 91, and whatever. So you see, the branch prediction rate is how important. Okay, so if your accurate rate is only 80%, 70%, then after 1 speculation, 2 speculations, 3 speculations, the new instructions are almost useless. Okay, that's why we care so much about the prediction rate. Okay, so now do you know how to preserve exception behavior? Whenever some instruction goes wrong, assuming this one, then what I need to do is simply to kill all this. Simply kill all this. Okay, these instructions are still running around in here. Do I need to go and kill those instructions in the CPU? Well, if you're fast enough, good enough, you can try to do so. But if you're not, don't worry. Whenever any instruction wants to commit, it will have to come to this table and look for itself first. If it cannot find itself anymore, then it cannot commit. Okay? And all these instructions need only to carry the index of itself in this table, which could be only a few bits. So for the ancient Pentium, there are 40 entries. 40 entry translates into 6 bits, not too many. Okay? Got the idea? Finally, how do we call this thing? Do you know the purpose of this mechanism? Preserve the order of original program execution. So give me a proper name of it. A name which you have already heard of.
Program order.
What?
Program order.
Not the correct name for some mechanism. Okay, this is a real thing, a physical thing. Every table needs to be looked up. Doesn't mean too much to me. Okay, you have heard of it. Reorder buffer. See, it reorders all the instructions running around in any random order in the CPU. Okay, so example, we don't need to look at this example anymore. Okay. Okay, so far you have any questions? For this case, yes, you need to wait. For this case, no, you don't need to wait. Wherever something goes wrong, just evict anything afterwards. Later, if this goes wrong again, and even older instruction goes wrong again, do the same. Okay, so you don't need to wait.
And once that happens,
Wherever I start to evict the instruction, I restart from there. Restart fetching. Okay. Any other questions? What you're talking about is totally up to the implementation of the operating system. Some of you may not get his question. I'll repeat it for you. Now, first, this thing is called reorder buffer. And then what his question is, we're executing instructions in the program. Okay, suppose this is the time axis. And at any instance of time, the OS may come in and ask for some services from the CPU. Okay, what we can do is, first we can evict the whole thing if this is a high priority interrupt. Or we can wait until this reorder buffer all commits if it's a low priority request. Okay? Okay, what if it's a high priority request and we want to stop execution? First, I told you, evict everything. But then there comes the second thought that, could I preserve what I already have? Or even preserve the contents of all the pipeline latches? Could I? That all depends on you. Okay, if you want to preserve all these contents, then your context switch becomes slower. Or if this service request is due to a power failure, then preserving all these means nothing because you will not continue execution whatsoever, right? If it's a power failure request, maybe you discard everything. Maybe it's a simple context switch. Then maybe you want to preserve the contents or discuss everything. It's up to you, or it's up to the OS choice. Okay? Did that answer your question? Okay, good. Any other questions? Data flow, actual flow of data values among instructions that produce results and those that consume them. Okay, so data flow means producer-consumer relationships of the instructions. Okay, branches make the flow, instruction execution flow, dynamic. Determine which instructions are supplier of what consumers. Example is, here we produce value of R1, and this branch determines whether this is the consumer or this is the consumer of the produced value. Okay, so they both are potential consumers. In static analysis, they both are consumers, but in dynamic behavior, only one will become the real consumer. Okay, so when I say consumer, sometimes I may say, no, this is not a consumer. Okay, but statically it is. So when you talk to compiler people, or when you talk to the architecture people, you might use different vocabulary. Okay, so you understand. Using of vocabulary is very important in your professional career life. Yes? Because I may continue execution on this path or on that path to the L. Okay, because this is a two-way branch. And this is the follow-through, this is the target of the branch. Okay, skip this one. Okay, computer is the news. It's no more news. You want to listen to the 6 years old news? So all these president or vice president of United States said this. Again, I repeat to you that if we can remain the most competitive nation in the world, it will benefit the worker here in America. People have got to understand when we talk about spending your taxpayers' money on research and development, there is a correlating benefit, particularly to your children, not right now to you, but maybe 10 years, 20 years later to your descendants. See, if it takes a while for some of the investments that are being made with government dollars to come to market. I don't know if people realize this, but the internet began as the Defense Department project in 1960 something. First internet, the ARPANET. Okay, so it did take a long while. So that's a Defense Department project to improve military communications. In other words, we were trying to figure out how to better communicate. Here was research money spent, and as a result of this sound investment that was a successful one, the internet came to be. So the internet has changed us. It has changed the whole world. Okay? So what's the sound investment we're putting in today? I don't know. At least a very obvious one is we are spending money to educate you guys. Okay? So pay attention in the classroom. Okay, loop unrolling. Should we continue on or should we have a 10-minute break? Okay, only one student requests for a break. So I'll continue. Okay, so software technique. This is a software technique. You will change your machine's program. Okay, so originally what you have is this. Code, loop. This branch is a branch back if, right? Loop control branch. Then you will want to change this to what? You will want to change this to okay, loop, whoops, maybe I should use yellow. Sorry, no yellow. Loop prime. Okay, this is no more the original loop. And now you have this, right? But duplicate it, say 3 times. Okay? And then this branch if, branch back if becomes, well, I'll simply write down 1/3 of times you will branch back only. And remember, you may have some remainders. Okay? So you need to have some makeup code. Okay, so the red part becomes this. What does the makeup code do? Suppose originally this will iterate for 98 times. So divide by 1/3, or divide it by 3, you will get 32, right? And you need to do the iteration 2 more times. Or divide it by 3 and round up, you will get 33. 33 times 3 will be 99. You did it 1 more time. So you need to undo 1 last iteration. So either this is a makeup or this is an undo. Usually doing makeup is easier. Doing undo sometimes is impossible because you already contaminated some storage location. And there's no way you can retrieve the original value. Okay? So usually when we divide it by something, let me make a remark. We usually do truncation. In other words, discard anything after the binary point or decimal point, whatever you like. Okay, we usually do truncation. Okay? Okay, that's a preview about loop unrolling. I'll come back after 10 minutes. Oh, I need to tell you, I need to be somewhere at 12:30. So I'll dismiss the class at 25 after 12, okay? I'll dismiss the class earlier today. Well, in fact, I'm too slow. I need to speed up. And as you can see, all the complications, once you understand the purpose, what difficulties we're facing, and the philosophy of our solution, our approach, then all the complications become very systematic. and easily understandable, right? So don't try to memorize. Try to understand it and lead the details to your own practice, okay? Okay, so software technique example, we have these high-level statements. And when you rewrite these to assembly code, compile it into assembly code, you'll see not only the basic block is small, but also the data dependencies. Okay, but don't cut in the middle. Okay, let's come back to this example. What's your question? Okay, yes or not, okay? But sometimes you can guess even though you don't know this is called upper bound of the loop index. Even if you don't, usually you can guess. There are always software and hardware approaches. Okay, whichever is more appropriate. Right person knows how to choose the right tool. Okay, not only is the loop body too small, but also, as you can see, this is a load. But also the loads will incur longer latency, incur more serious data hazard. Okay, so assume following latencies for all examples. Ignore delayed branch in these examples. If the producer is floating point ALU operation, assuming all the array elements are floating point, this is scalar. Scalar means standalone number, okay? Array means a series of interrelated numbers, okay? But also the scalar is floating point. So if the producer is floating point ALU, then consumer is floating point ALU, then the consumer needs to wait for 4 cycles in addition to 1 cycle, which is assumed to be, of course. Okay, so for every ALU operation, you need to wait for 1 cycle, right? For the floating ALU producer to floating ALU consumer, you need to wait for 4 additional cycles. Okay. Oh, I'm sorry, it should be 1 plus 3 additional cycles. Okay, so for this one, it's ALU producer and store double consumer. Then the latency will be 3. So the additional store cycles will be 2, and so on. Okay. Having this assumption, then our assembly code or machine code rather, these are actually machine codes. They have 1-to-1 mapping to machine codes. Remember I told you, assembly statement to machine instructions mapping could be 1-to-1, the most common case, but could also be 1 to any number of instruction codes, okay? So we assume that these are machine codes in assembly form, in symbolic form. So after this load, we need to have 3 store cycles before we can add, before we can use the value produced by this instruction. Okay, and so on. So in real execution, whoops, I'm sorry, only 1 store cycle, and then 2 store cycles. If the producer is ALU and the consumer is also ALU, then we need 3 cycles according to the previous table. Okay, so during execution, this sequence shows the real timing of execution. we also indicated where the stall cycles should be inserted in. And these are just the reminders copied directly from the previous table. So for every element, we need 9 clock cycles to handle it. Can we rewrite code to minimize stalls? Yes, we can. We do load first and don't do add immediately. We adjust loop index first to fill the stall cycle, which should have been here between load and add. Okay? And here we have no more independent instructions to substitute in, so there will be 2 stalls. Cannot eliminate them. By doing this, we have 7 clock cycles wasted, not used for 1 array element. But just 3 for execution, and the other 4 are for loop overhead, including stalls, including loop control overhead, 2 and 7. These 2 are simply for loop control. Can we make our code faster? Oh yes, here we rewrite the loop to minimize stalls. We have unrolled the loop body 1, 2, 3, 4 times. Okay, with 4 times and unrolling, there will be no more stalls needed. And the loop control overhead is still 2 instructions only. Okay? But the number of iterations get reduced to 1/4 of the original number. Okay, so when we adjust the loop index, what did we do? We changed that from 8 to 32? Forgot. Previously, it should have been 8. Okay? Now, we have spent 27 clock cycles, but we have handled 4 array elements. So on average, we spend 6.75 cycles on each element. Okay, so that's how we do loop unrolling and how we can get profit, get benefit from loop unrolling. Any questions so far? It has to do with that. We make that assumption and then derive these latencies. Okay, so these assumptions should have not been assumptions, should be the real numbers. Question? Right. Even with forwarding or without forwarding, those numbers will be larger. Question? Okay, what you have seen is not the entire truth. What's the entire truth? The entire truth is if it iterates for n times, then how many times should you unroll? What if this n is a weird number like 73? 73, you should divide it into what? Difficult to tell. Number 2, how many times do you need to unroll in order to eliminate all the stalls? If you can unroll it for 3 times to eliminate all the stalls, do you want to unroll more times? Do you? No? Come on, be more aggressive. If I unroll more times, what benefits will I get?
How many pipeline levels you have?
Oh, really? Is that the only consideration that you can think of? If I unroll more times, then the loop overhead can be amortized by more iterations, right? So do you want to unroll more times? Does that give you a motive to do so? Yes. But then what disadvantage would that bring you? See what's wrong with this result. Yes?
It uses a lot of registers.
Right. It increases register pressure. Have you noticed? The loads must have different destinations. Okay? They no more use the same destination. Otherwise, output dependence will persist, and you cannot have additional parallelism. What else? What?
The code size.
Right, the code gets bigger, wasting memory and instruction fetch bandwidth and decoder power. No. Instruction fetch bandwidth may remain the same. Decoder power may remain the same, but you used more memory space. Okay. What else? Okay, you mean
We are gaining some performance there.
you mean the compiler has to work harder.
For example, yes.
Okay. Well, usually that is offline. And in typical application case, once the code gets compiled, it will be used billions of times. So usually that overhead is okay. Okay, usually we don't care too much about compiler overhead, as long as compiler has that capability to do better job. What else? Okay, the remainder part, in our case, this is not shown. Okay. It could not, may not be able to be divided into an integer number. Okay. The details, the issues, number one is, first, we do not usually know upper bound, and then suppose it is n, and we would like to unroll the loop to make k copies of the body, the code becomes larger, and we need to have prolog or epilogue. In other words, the code before or the code after to handle the remainders. Okay? And then, instead of a single unrolled loop, we generate a pair of consecutive loops, one loop for handling the remainder, the other is like to replace the original loop body, but this time it becomes bigger, unrolled several times. This part to handle the remainder is usually not unrolled. It is still like the original code. Okay? And this usually handles what? 0, 1 portion or n-1, n-2 portion? I don't know. It depends on which way makes you be able to easier index your vector elements. Okay, it has to do with the data structure you're dealing with. Okay. So you might want to use prolog, you might want to use epilogue, whatever. So for large values of n, most of the execution time will be spent in the unrolled loop. Will be spent on this part, the unrolled loop. So you still gain a lot of performance. Unrolled loop that minimizes stalls will be like this. 14 clock cycles or 3.5 per iteration. So we have refined the code one more time. Okay, we have arrange the order of the machine instructions. Remember, I continue to emphasize these are supposed to be machine instructions, not just assembly instructions. Okay, so 5 loop unrolling decisions. How many times do you want to unroll the loop body? Okay, so let's see. To make the decision, you need to understand how one instruction depends on another. In other words, you have the data dependence graph. Plus, the data dependence graph looks just like a control flow graph, but every node is now instruction I plus 1, and so on. And you still have a graph like this, something like this, okay? And on the edge, you may want to specify the latency between the consumer, producer-consumer. Okay? This means how many stall cycles you will need to insert in your code to show how it's actually executed. Okay? So the issues will be determine loop unrolling useful by finding that loop iterations were independent. Sometimes you cannot do unrolling, or doing unrolling will not help you at all, because iteration I is data dependent on iteration I minus 1. Okay? And then use different registers to avoid unnecessary write after read, write after write dependencies. Eliminate the extra test and branch instructions and adjust the loop termination condition. Determine that loads and stores in unrolled loop can be interchanged by observing the loads and stores from different iterations are independent. This is actually, again, data dependence relationship analysis. And then schedule the code properly to make the execution cycle count as small as possible. Okay? Okay. Are there limits to unrolling? Yes. Okay, so there is still branch control overhead, loop control overhead, although it can now be amortized by more iterations, more original iterations. The code size will become larger, and the registers to be used will become more, and loop unrolling reduces impact of branches on pipeline. Another way is branch prediction. This is not a limitation, but this is just to tell you loop unrolling can be done by hardware also. Okay, this is not one of the limits. Okay, static branch prediction. We have entered into a new topic, which is branch prediction. Okay, we're done with the previous topic. Okay, throw every trash in your mind away. We're going to talk about something new. Before that, any questions so far? Question? Question? Okay, so now we talk about branch prediction. Okay. Recall your memory. In lecture 3, we showed scheduling code around delayed branch. To reorder code around branches, need to predict branch statically when compile. In that delayed branch code scheduling, remember we can move instructions in the same basic block down to replace the no-ops, delay slots. Or we can move instructions from the target or from the fall through. Each case will have different considerations. Remember that? Okay, so whether we want to move instruction from target or the fall through from to replace the no ops delay slots depends on whether we think this branch will be a taken or a non-taken branch. Okay, so we need to have some static knowledge of that branch instruction. Or if no knowledge, at least you need to have judgment. Okay, so the simplest scheme is just to wait. The simplest scheme is to predict a branch as taken. I don't think so. I think the simplest scheme is just to assume it's not taken. So I don't even know its existence. I just go ahead with my fetches and decodes, right? That's the simplest. So IBM did that in a very early product. So in other words, they did nothing. But when the salesperson came to the engineer, the designer, and asked him, hey, what did we do inside CPU? The engineer was honest. Usually the engineers are honest. So the engineer said, I did nothing. I simply naively go ahead. And if anything goes wrong, I kill those instructions. Salespeople are usually wiser guys. So the salespeople made a suggestion. Why don't we tell our customers we did speculation, and the speculation we did is not taken? You see? So the simplest scheme is predicting not taken, but a smarter scheme would be to predict it as taken. Okay, because this gives us higher accurate, higher hit rate. Because usually branches were taken for 70% or even higher of the time. Okay. So these are the benchmarks. This is a statistics of the misprediction rate if we do this prediction. Whatever, this is not important. Okay, so more accurate scheme predicts branches using profile information collected from earlier runs and modify prediction based on last run. So what is this? What does this mean? This means we can do even better. We can observe the behavior of every individual branch instruction and make customized prediction for each branch. Okay, so in your program, this guy always takes. This guy always not takes. Okay, how do you know? By running some sample data or examining the history of some profiled information. Okay. Now tell me, is this method done by compiler or by hardware? You need to be able to at least make this judgment. Hardware? Anything else? The answer is can be by both. Okay, if it's compiler, then you need to have a big trace file showing what this branch did last time when I benchmark it. Or if it's hardware, then every time you encounter this branch, you update your record saying it used to be like this. Okay, both are possible. Okay? So this profiling, don't think it's only useful for static analysis. It can be dynamic. Okay, why does prediction work? Because we the algorithms that we design usually has some fixed behavior pattern for every instruction. Like for add instruction, the behavior never will change. Add is add, add is add, right? But remember, sometimes we want to predict the value of this addition. Do you know how to predict the value of the addition? X plus y, guess what the value will be? You give up? Okay, you're laid off. Okay, if you want me to predict x plus y, then I'll look back into my history and say, oh, y is a constant, 1. And x has never been updated by other instructions. So if x was 5, 6, 7, 8, then I'll predict it will be 9 this time. Okay? See that? For some add instructions, value prediction is even very simple. But if x comes from memory, y also comes from memory, then maybe there's no way. Okay? Maybe. I didn't say no way, there's no way. I didn't say always there's no way. Okay? So now you see, sometimes the underlying algorithm makes every instruction to exhibit some regular behaviors, and data that is being operated on has regularities, and instruction sequence has redundancies and artifacts of way that human compiler think about problems. Is dynamic branch prediction better than static branch prediction? The answer is definitely yes. Because for static prediction, usually for a certain branch instruction, we can predict only always taken or always not taken, right? It's difficult to make prediction changes for the static method. I didn't say no way, but I say it's very difficult. Because then it must be based on some dynamic behavior. Then is this method static or hybrid? Hard to tell. Okay? Or if it's hybrid, then it depends more on dynamic part or more on the static part. Then most people will say it depends more on the dynamic part, because the dynamic part still can manipulate, yet the static part is done. It's gone. No more effect anymore. Okay? So it seems to be definitely it is. The answer should be definitely. There are a small number of important branches in programs which have dynamic behavior. So dynamic may be superior to a static method. Okay, so for static, I already told you, for certain branch instruction, you always predict it to be taken or not taken. Even though, say, let me give you an example. This is my main program. This is a subroutine. And within this subroutine, there's a branch F. Okay, this branch, when called by this guy, may be not taken most of the time. Whereas when it's called by this guy, may be taken most of the time. So statically, how should you predict? Difficult. Right? Difficult. But dynamically, it's much easier and more accurate. So that's why we will focus on dynamic branch prediction. Let's continue on. So we know performance is equal to the function of accuracy plus cost of misprediction. No, not only that, this equation is incorrect. Tell me why. Accuracy, that's important, of course. And whenever you're wrong, you have to pay some cost. But anything else? Anything else? Yes. Okay, so that has nothing to do with performance. Performance means the number of cycles, right? So even if you need to have a big data structure somewhere, it doesn't affect the time unless It does take up some time. What? Your focus is what? Still time, not hardware cost, right? So he somehow gave us the answer. Performance also has to do with how much effort you have to put in order to make prediction, right? It's just like a chess game. How long do you have to ponder? Usually for some chess game, one move will take like overtime in order to decide. Okay, so watching such a game is very boring. You always have to drink Coke, nothing to do, nothing changes. Okay, so in order to make the prediction, how much time you need to spend, that has to do with prediction, with performance. For instance, this is my execution timing branch if, and after 4 cycles, then I know whether I should fetch from for through or target. Looks like false and true. Then I already know how to fetch from for through or target. And perhaps you want to be smarter. You want to predict. So you begin to predict, but it takes you that many cycles. Do I still need your prediction? No. So in-time prediction is very important. Okay? Okay, so we know there are mistakes in the textbook. And we caught one just then. Okay, so branch history table is one data structure that we use to help us predict. That table uses lower bits of PCE address to as the index and stores 1 bit to record how did that branch behave last time when it's executed. Okay, so this table is like this. Maybe 1024 entries indexed by the lower 10 bits of your program counter. And records whether that branch was taken or not taken last time. Okay, very simple data structure. What if in my program, 2 branches have the same lower portion of PC, in other words, address, and share the same entry? What happens? Tell me.
Skews the results.
Won't hurt because it's prediction anyway. Perhaps they have the same previous behavior, so maybe it won't even affect my accuracy. Okay, but the size of the table will have to be limited. How large is the program? Theoretically, anywhere within 4 gigabytes. Okay, so how big should this table be? Depending on your instruction size. In the worst case, 4 gig entries, which is way too big. Where do we store this table? When we talk about dynamic, then this table better be not in the main memory. Okay, usually it's right in the CPU. And CPU can tolerate a table of maybe 8K byte, maybe okay. Okay, but bigger than that, maybe no way. Okay, yes?
So this table is
You want to add the number of loads and stores? No. You want to put the reorder buffer in the CPU or in the memory? It's your judgment. Okay, you want to know the current status? Nobody puts that in memory, too far away. Plus, the OS doesn't have to know that. Okay, does your OS care about what CPU you are using? Does it care? It will be better, but usually it's independent. Okay? Okay, so you know what this table is and you know how it's used. No, you don't know how it's used yet. Remember, the prediction should be made fast. How to make the prediction fast? Okay, so this would be my pipeline. Fetch, decode, remember this thing? Okay, when I fetch, in fact, I send PC to my instruction cache, right? I can, in the meantime, send the PC to my branch history table. Can I not? Just make the fan out to be 2. Okay, 1 to access cache and 1 to access this table. Guess which one will return the results first? History table, it's a lot easier. Okay, it never misses. It's a very small table. It doesn't need to do tag match and the line, a byte selection within the line. It doesn't have to do all those. Okay, so whenever the instruction in, you already know if it's a branch instruction, or if it is, then whether that it should be predicted in what way. You see how in time that can be. No delay, then you can begin to fetch from your predicted path. Right or wrong? Tell me if I said that right. Then you can already fetch from the predicted path.
Don't you have to change the PC?
What?
Don't you have to change the PC?
Correct. If I predict it to be taken, then how do I know what the target is? Oh, right. I need to know the target if I want to branch. Okay. If that's the case, no sweat. Then I append my target here. Okay? No sweat. Okay, with the target, then I do need to have 1 extra bit called the valid bit this time, showing if that target is for real or just trash, right? Or even if I want to be more precise, maybe I also need a tag, because 2 branches may share the same entry. So I might like to know which target, which branch this target belongs to. Okay, what if I don't have this? That's fine, it's just like a wrong prediction. Remember, the path and the target both are important information for branch prediction, right? This indicates the direction, predicted direction. This could be wrong. This could be wrong. This could mismatch. Or it could be invalid. In other words, this is the first time I see this branch. Okay? No problem, it's just prediction. I must have some recovery mechanism to make things up if anything goes wrong. Okay? I'm done with the whole topic. Any questions so far? Okay, but 1 bit direction prediction has some deficiency. Let's see. The portion of a program that takes up most of the execution time will be the loop bodies. So we care about loop branch prediction accuracy very, very much. Okay, for loop branch of instruction, it will be taken, and then not taken. And then taken, and then not taken. Okay, repetitively. Okay, so if we use 1-bit prediction, first, I don't know. So maybe I'll arbitrarily predict not taken, but it doesn't matter, whatever this would be. And then I'll predict taken, 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 based on the previous result, right? I have 1-bit record. So this would be taken, and I made one mistake. And then not taken, and then I made another mistake. So for every time the loop is visited, I'll make 2 mistakes. Why is that? Because my prediction mechanism is too sensitive. How do I correct this problem? Okay, people begin to think. Okay, one thing's always true. If you use more bits, then you can record more information, right? So can we use more bits? Okay, give it 1 more bit. Now I have 2 bits. These mean bit locations, not zeros. Okay, with 2 bits, then I will have 4 different combinations. One combination is called strongly not taken, and then weakly not taken, and weakly taken, and strongly taken. So I have these 4 prediction possibilities. Whenever a branch is newly encountered, I enter into this because most branches tend to be taken branches. Okay, so most branches tend to be taken. So whenever a new branch is encountered, I enter into this state. Next time when I see it, if it's not taken, then I do state transition. Remember state machine? It's a counter. Okay, now we have a 2-bit counter. Whenever it's not taken, I go this way. Whereas wherever there's like if I see this branch to be not taken again, then I stick into this state. However, when it's taken, or taken, then I do this state transition. So can you see? Now we have 4 states named strongly taken, weakly not taken, strongly not taken. These are my prediction outcomes. Whenever I see a taken, I have more confidence towards this end. Whenever I have a not taken, I have more confidence towards this end. And if I use this state machine, then the result will be taken. You see, when I first encounter it, I already used taken prediction. Taken. And here, not taken, doesn't matter. My prediction will still be taken, because one not taken will not switch me into the not taken prediction side. Okay? So using 2 bits, I'll be wrong for only once. Improvement. Do you want to make it even better by using 3 bits? But if you use 3 bits, then this predictor will be too insensitive. Okay, so 2 bits are almost the method everybody uses.
So by default, it's always weakly taken.
Wherever a branch is first encountered. What's wrong with that method? No good. Because even if you say it's taken, you don't know what the target is. Okay, even if the direction prediction is right, doesn't help. Got it? Okay, so target is also very important. Any questions so far I need to run? See you then.